A storm is blowing in, and the ledger keeper is up late. She has to write out tomorrow's work orders tonight, long before the sun comes up. The problem is, she has to do it without knowing tomorrow's numbers. How many fallen poles will the river wash down by morning? Nobody knows. How many helpers will arrive from the South Lodge to help rebuild? Nobody knows that either. It seems impossible to balance a mathematical ledger when the core numbers are a complete mystery. You can't add or multiply thin air. But the keeper dips her quill anyway. She knows a secret. You can use a letter to hold the exact place of a number you don't know yet. It creates a physical hole in the math, keeping a space warm for the real data. By giving the unknown a name, the keeper moves beyond simple arithmetic to build the logic she'll need long before the data actually arrives. Take the first work order, accounting for those river poles. We'll use the letter P to represent whatever number the river eventually brings down. There's a standing rule at the dam. No matter what washes up, 6 poles are already safely braced in place. So tomorrow's total bracing stock is written out as P plus 6. When morning breaks, the river delivers exactly 9 poles. That number simply drops into our waiting letter. 9 plus 6 gives us 15 total poles ready for the dam. But if it had been a heavier storm and 20 poles washed down, the ledger is still perfectly prepared. 20 drops into the slot, and we immediately see a total of 26. The expression P plus 6 functions as a mathematical machine. It sits ready for input, generating the correct total the moment the missing data drops in. The second work order is slightly more complex. It accounts for the southern helpers hauling wood up to the dam. The keeper needs to track the total haul. She knows each arriving helper can push 3 bundles of branches. That's a rate. She also knows her own crew works independently, hauling a constant 10 bundles no matter what. We build a structured expression for this. Let H stand for the number of helpers. The math becomes 3H plus 10. Read it back in plain words to check the logic. 3 bundles for every helper, plus our guaranteed 10. Every piece of that written expression corresponds exactly to the physical work happening in the pond. By dawn, 4 helpers arrive. The number 4 drops into the H slot. 3 times 4 gives us 12 bundles from the helpers, combined with the 10 from the local crew, resolving to 22 bundles total. Notice how a variable can be multiplied by a rate. This lets a single line of math capture the interaction between multiple moving parts and constant rules. The final work order requires calculating the crossing fee for a ferry raft transporting young beavers across the pond. We'll let the variable W stand for the riders. The fee is strictly 2 acorns per rider, but there is a physical limit. The raft can only safely carry between 1 and 8 young beavers. Here, W is entirely different. It isn't a single mystery number we are waiting to solve. It's an entire range of legitimate possibilities. If the raft takes 3 riders, the output is 6 acorns. If the raft is fully loaded, hitting the absolute maximum of 8 riders, the output is 16 acorns. Writing down the permitted stat, the boundaries of the variable, is an essential part of the variable's meaning. It guarantees the math rule won't try to predict impossible situations, like cramming 50 beavers onto a tiny raft. The storm passes and dawn arrives. Out on the water, the math rules built in the dark are working flawlessly in the daylight. The expression P plus 6 perfectly braced whatever the river gave. 3H plus 10 calculated the exact haul no matter who showed up to help. And 2W collected a fair, accurate fee for every legal ferry load. The letter holds the place. The expression holds the rule. Once you understand that, you have the ability to write tomorrow's mathematics tonight, securing the answers before you even have the numbers.